Hello out there, and a warm welcome to this last conference session block within our world of electrification and automation. I am still Michaela Mönikes, and I am ongoingly happy to guide you through our interesting content. You can even access all recordings of the previous presentation. And now our digital conference continues with our next speakers. It was planned to have Klaus Wagner and Kerem Bayram here on stage, but due to personal reasons, Klaus cannot be with us here in the studio. Fortunately, we did some rehearsals last week and we have a recording of what Klaus tells. So you will see a mixture of a recorded presentation and then we have the live version because Kerem is here with me in the studio. And the two will talk about measures to reduce the effects of arcing faults in air-insulated medium voltage switchgear. Please feel free to post your questions at any time during the presentation, and we will try to answer as many of them as possible live at the end of the presentation. Well, it might be that we can answer only parts of the question because Kerem is my specialist for the sequence and Klaus Wagner is addressing a different topic. So nevertheless, ask your questions. We'll see if we can answer them right here in the studio, and if not, we will answer them via mail. So make intensive use of this possibility to directly address the experts. We are here for you. And one question has always the same answer. Yes, we do record the session, and yes, you do get access to the recording. So Klaus will start and focuses on improving equipment availability. And so the auditorium will get the possibility to learn about measures to reduce the effects of arcing faults. So we start with Klaus.
Hello and welcome to this presentation about Siemens arc protection solutions. Today we will present you two different approaches. One which clears the electric arc with a standard circuit breaker of the switchgear. The other uses extra equipment to limit down the arc burning time to only a few milliseconds and therefore limit dramatically the destructive effects of the arc. My name is Klaus Wagner. I am promoter and technical specialist for SIPROTEC relays, and I will present you the first solution. I do not need to say a lot of words. I think the pictures are self-explaining. If an electric arc is not cleared early in a switchgear, then it will destroy the cubicle. Better not to imagine what happens to people who stand close. Below is a picture of some protective clothing. What has accumulated on the overall is material from the switchgear, like for example copper, that evaporated and condensated on this piece of garment. When an arc starts, we basically distinguish two phases of destruction. What is shown here is a record of the pressure inside the cubicle. We see the main peak occurs after approximately 10 milliseconds, and then the pressure decreases again because the safety flaps of the switchgear start to work. After approximately 100 milliseconds, the thermal damage starts to become considerable. If we now think about a standard protection system with a circuit breaker operating time of about 50 milliseconds, it is clear that we cannot eliminate pressure damages. However, what the standard protection system can achieve is to clear the fault before the thermal destruction phase becomes significant. This means the fault must be cleared before 100 milliseconds. Here we see some impressions of arc destruction in a cubicle. The reached temperatures are extremely high. The cubicle and probably adjacent cubicles need to be replaced. The aim of applying arc protection is to bypass grading times, especially interesting in the medium voltage or distribution level, where normally there is no dedicated fast operating busbar protection. The shown example is a simple time grading example for a radial network with 4 stations. The relays in the feeders cannot communicate with each other, and the fault at the end of the far right side, on the far right side, is seen by all the relays. To get selectivity, the upstream relay has an additional delay time on top of the next one downstream. In this way, the delay times add up, and the relay at the in-feed has an unacceptable long fault clearing time of 900 milliseconds in this example. But even if you use better protection principles, the busbar is not protected in fast time if no dedicated protection for it is installed. The goal of the arc protection now is to understand that the fault is locally in the switchgear and not far away downstream, and so be able to cut off the delay time to a minimum. For this, we have the possibility to add sensors that detect arcs via the abrupt increase of light. What we need? A SIPROTEC5 device. This can be one of the expandable devices, or also out of the 82 family, our non-expandable SIPROTEC5 branch. An empty slot for a plug-in module in the base device, or on the dedicated CB202, which provides additional 3 plug-in slots. Our arc protection module, which has connection points for up to 3 sensors. And finally, the sensor itself. We have 2 types of sensors. A point sensor, which can be placed in one compartment of the switchgear, or a line sensor, which can be placed, for example, along the complete busbar, which is a cost-optimized solution because faults on the busbar need to be cleared always by the in-feed circuit breaker or breakers if we have more in-feeds. Where the point sensor comes as one item, including the sensor mounted on the supply line, the line sensor needs to be ordered in 2 parts. The first part is the sensor itself, a transparent fiber, here on the right-hand side in the below picture, which catches the light, and the second part is the supply line, which is insensitive to light, so that it can be placed wherever necessary, without the risk to contribute to a light pickup. In this way, also a visitor group taking eagerly pictures with flashlights cannot trip the circuit breaker. Each sensor consists of 2 fibers because we built in a supervision of the sensor. The arc module sends permanently a light telegram into one fiber and inspects to receive this telegram on the other fiber. If the fiber is interrupted, then the SIPROTEC5 relay gives an alarm. Where can optical sensors be placed? We see here an example of a Siemens NX-Air switchgear with 3 separate compartments. The SIPROTEC5 relay has 3 sensors on each module. 1 for the busbar, 1 for the breaker, and 1 for the cable connection compartment. The light sensor is extremely fast and reacts within less than 5 milliseconds. However, there's a risk remaining for wrong pickup caused by photo flashes or arcs in the next feeders. Therefore, with our SIPROTEC5 devices, we can additionally combine the light pickup with an overcurrent detection. The combination of 2 independent methods increases reliability. The disadvantage is that for most of the fault locations, the in-feed breaker needs to be tripped instead of the local outgoing feeder circuit breaker, and so a lot of sensor wiring to the in-feed device is necessary, and also the number of feeders is rather limited, if not a second device for more arc sensor inputs is placed at the in-feed. A clever way to overcome this situation is to combine light, current, and communication. The relay communicate the local pickup or the current pickup at the in-feed to the other relays, which take both signals in combination to trip the circuit breaker. The advantage is again the higher reliability, and that doing so, the 3 sensor inputs of one module in each feeder is enough, and so the number of feeders overall is not limited. Here's our switchgear consisting of 1 in-feed and 2 outgoing feeders. These are equipped with point sensors in the breaker compartment. The in-feed relay is responsible for the busbar and equipped with a line sensor along the busbar. If an arc happens in the breaker compartment of feeder 1, the point sensor of this device picks up and sends this light pickup signal to the in-feed device. In the in-feed device, the light pickup is combined with a local current pickup, and only in this case the incoming feeder circuit breaker is tripped. The fault cannot be tripped locally because, as indicated in feeder 1, if the fault is upstream the circuit breaker towards the bus bar, the local circuit breaker is without effect. On the other hand, for faults in the cable compartment, tripping the local circuit breaker is selective. So we have also point sensors in the cable compartments which pick up on an arc there. The incoming feeder protection sees a current pickup and send this to all outgoing feeder devices. Our feeder 1 relay combines the local pickup with the received current pickup from the in-feed, and in case both signals are active, it trips the local breaker, which is a selective fault clearance. It is mandatory to evaluate the current in the in-feed because faults in the local cable compartment, which are upstream the current transformer, as indicated, are not seen by this current transformer. So this is only roughly a part of the principle of light and current detection combined with communication to give you a first impression that we can set up a clear and powerful solution. Concluding, I would like to summarize. With a classical circuit breaker, we cannot avoid the damages coming from the pressure, but we can avoid damages in the thermal phase. With a circuit breaker of 50 milliseconds operating time and a protection function that works below 15 milliseconds, we are far away from the target of 100 milliseconds. So this was my overview of circuit breaker-based arc clearance with a standard protection device. Now I hand over to my colleague Kerem, who will explain you our second solution for arc fault protection.
Thanks to Klaus for having the introduction on the best conventional method for arc flash protection in medium voltage air insulated switchgear with SIPROTEC5. Good morning and good afternoon to all attendees. My name is Kerem Bayram. I am one of the product managers for medium voltage air insulated primary switchgears of Siemens. I would like to carry the topic of arc flash protection one step further and introduce you a state-of-the-art solution in the range of active arc effects mitigation measures. The occurrence of an internal arc fault in a well-designed, type-tested, correctly installed, and operated switchgear is improbable, but not impossible. The reasons are mostly linked to human interference or environmental causes. Most repeating causes are loose connections, corrosion causing overheating and further escalating to arcing faults, rodents and vermin entering into the equipment, or deteriorating insulation in time. Many of you should have seen kind of disaster videos showing arcing faults and their consequences over human beings or on the equipment and its environment. What you have seen there is an explosion with a dense light, fire, and smoke. What happens inside the equipment is actually beyond those you have seen. Here we are talking of temperatures exceeding the sun's. Copper in the thermal phase expands by a factor of 60,000 times when it transforms from solid state to plasma formation. The high pressure, which can easily rupture eardrums and collapse lungs. The level of sound associated with the pressure, which can exceed 160 decibels. Material and molten metal expelling at speeds exceeding 1,000 km per hour, fast enough for a shrapnel effect to human body. Accordingly, possible consequences on the equipment, processes, and human beings are various. An internal arc classified switchgear can prevent operator injury under normal operating conditions, which is the status where all doors and covers are closed as per IEC. But it does not protect the equipment from damage and prevent the occurrence of secondary hazards like pressure wave, sound blast, blinding light, fire, toxicity, contamination, and etc. And coming back to the definition of normal operating conditions, this is not always in line with the necessities of real life, right? Just imagine a simple maneuver where a high voltage door is opened to take the circuit breaker out of the panel for a periodic maintenance, and the busbar is live. This is what an LSU2 type service continuity category offers for. So what about the safety in such status? In the case of an internal arc, priorities are clear to every of us. First is to protect the personnel, as it may endanger their lives. Second is to keep the equipment and related connected processes available, as it may lead to substantial economic losses for businesses. System engineers are in a dilemma. They should find the optimum balance in between the best possible coordination settings to minimize the effects of unplanned shutdowns. Maybe you remember the slide of Klaus, where we came up to a tripping time of 900 milliseconds in that example because of the time grading scheme. And second, the best possible safety of personnel. And each usually means sacrificing the other. Within this dilemma, there are some parameters already fixed without room for adjustment. In regard to limiting the arc flash incident energy, there is also not much room to play. Amongst the parameters, it is the fault clearing time we can act on by utilizing fast tripping circuit breakers and early detection of arc via light or pressure sensors. What if we would have the chance to act directly on the arc itself? We have a solution, quenching the arc itself in 5 milliseconds after ignition of the arc, preventing the damage to the equipment due to arc flash, uncompromising safety even when the doors compartment covers are open, which is reusable, allowing to restore the service in a very, very short time without the need for replacing the equipment. You'll be watching a video demonstrating this solution in a nutshell. Then I'll be back.
Arc flash faults are the most devastating events in power distribution systems. In well-designed and type-tested switchgear, internal arc faults are unlikely, but not impossible. Mostly, they are linked to human interference or environmental causes. Typical internal arc classified switchgear can prevent operator injury under normal operating conditions. However, it does not protect the equipment from irreparable damage and does not eliminate all the secondary hazards caused by an arc flash. The damage-causing power supply and process disturbance may lead to substantial costs of millions of euros. The solution from Siemens is SIEMENS. It is a reusable active arc effects mitigating system, quenching the internal arc in sub-cycle times. In the event of an internal arc fault, it reduces the system repair time from days and weeks to minutes and hours, resulting in drastically reduced economic losses. Conventional protection methods do not provide fast enough protection capable of securing the assets, the safety of staff, and the availability of the processes. Once an arc fault is detected, SIEMENS, at almost the same time, consciously closes the main current path of the switchgear to earth. This creates a three-phase low-impedance parallel path for fault current to flow, thus extinguishing the arc fault right away. The internal arc is quenched in less than 5 milliseconds after ignition, long before the pressure peak and before the arc can cause any significant damage. It minimizes the damage within the switchgear due to reduced arc energy and pressure. Service can be restored rapidly, leading to minimized service outages. SIEMENS offers a state-of-the-art level of safety that goes beyond the standards. It minimizes repair costs. The faulty functional unit of the switchgear can be used again. It is reusable, capable of quenching 5 times without the need for replacement, and it is maintenance-free. SIEMENS offers constant reliability through continuous self-monitoring. It also has the capability to switch for testing and commissioning purposes without the need for replacement. Sequench, taking your switchgear to a higher level. It is available as a complete solution for Siemens switchgear. Siemens Sequench, your natural choice.
Sequench, in the case of an internal arc, by consciously closing the live bus bar over the ground bar of the switchgear, it creates a controlled, bolted short circuit path for the fault current to flow. This is the main current path of the switchgear and is actually the intended current path for such fault conditions. And it does that within 5 milliseconds after the arc is first ignited. By doing so, it prevents the damaging effects of an arcing fault and allows to re-energize the switchgear in a very short time, avoiding time-consuming and costly system repair activities. Words are meaningless when it comes to arcing faults. Here you'll see a video shot from one of our development tests with Sequench located in the busbar compartment of a 12 kV lineup. Arc ignition was in the cable compartment of the cubicle in the middle. Not that fancy, right? You see nothing, because the arc was quenched immediately after it ignites. Primary and secondary hazards are fully avoided. And the result, compared to the one without Sequench for the same fault current. No damage has been given to the panel when Sequench is used, and the same panel can be re-energized immediately after deleting the root cause of the fault. Arc fault is sensed by an arc flash protection system acting on light and overcurrent, which are the standard characteristics of an arc that make it safely detectable. Sequench is reusable, so the switching operation in the case of an arcing fault is reversible. Resetting is done from front of the panel without the need for opening any covers. It can withstand 5 consecutive switching with the full rated short time withstand current of the switchgear. It also allows for 30 real physical switching operations without load for testing and commissioning purposes. As of today, Sequench is available as a complete integrated solution into the internal arc classified air insulated medium voltage switchgear type NX Air up to and including 17.5 kV and 50 kA. It is located as fixed mounted in the busbar compartment. That is why only a single Sequench per bus section is required and enough for the protection. It is worth mentioning the explicit benefits of the solution. First is the improved safety, which is beyond the one defined in the standards, as it not only supplies safety under normal operating conditions, but also for maintenance maneuvers. Second is the minimized downtimes due to prevention of the damage given to the equipment. This not only leads to increased availability of the processes, but also help eliminate related penalties. Last but not least, elimination of the impacts on the surroundings, which in many cases being underestimated during risk analysis and life cycle related expenditure calculations, but actually takes a big role on the costs after an arcing fault. Overall, it is the reduced OPEX supporting the business. Thank you for your time and attendance. Now the speech is yours with your questions.
Thank you, Kerem. And I'm still glad that we had this recording from Klaus. And we have some questions from the auditorium. You can still type in your questions. Every question that we cannot answer right here, we will answer afterwards via mail. The first question is one where I will take the answer, because it's, do I get any certificate of participation? This is an open conference where we just share some information, not like a training or a webinar. So what you take with you is hopefully information about Siemens, but we will not provide a certification this time. If you join one of our dedicated webinars, then we have some that are certified or receive a certification there. Then let's see if this is a question for you, or it would have been Klaus to answer. We'll see. For medium voltage systems, sensors put on the bus bars compartments together with current measurements can be a valid substitute for bus bar differential protection that are not generally foreseen for this voltage level. Is the sensor valid enough to be considered as a valid substitute for the bus bar differential protection?
With my knowledge, I don't think so, but as you thought, better that Klaus replies back to this
so we'll
question.
take that question offline. And how do you apply this solution on ring feeder panels other than the bus bar? I think that's also a Klaus question, because it's on the configuration there. Okay, let's see. And then the question is it possible to use the technology on old switchgear or even on non-Siemens switchgear?
Oh, that's of course possible. Sequence has a withstand up to 24 kV and 50 kA. So as soon as it's properly integrated and the rules, requirements from the relevant standards are followed, theoretically it can be integrated in any medium voltage application. That's possible for sure.
Great. And we take one last question here in this online round, because I need to take a little bit care of the time. But this question is, do you avoid any type of damage to the switchgear?
The final fault clearance in our application is done by tripping the feeding circuit breaker. And this is normally under 100 milliseconds. So considering a type tested switchgear, which in case NX-Air, our NX-Air switchgear, it has a withstand for the full short circuit current for the duration of 3 seconds. So theoretically, the switchgear, the main current path of the switchgear, can withstand 30 times the stress which is created by sequence. Therefore, yes.
Great to hear that. So thanks a lot for your questions until now. If questions come to your mind later, or if we didn't answer enough, you are invited to join us in the exhibition part. And there we have this Meet Us in Teams button. If you click on it, our receptionist will meet you in a larger Teams room and then guide you into one-on-one discussions with our experts. So there might be more people in it, but you will find a dedicated slot just with the expert in there. I think Kerem is not yet there, but we have other specialists talking about these measures, about reducing the effect of arc fault in air-insulated switchgear. So still open questions. We have two. We will answer later on if we have Klaus back on board. And now I'm looking forward to see you in one of the next sessions. The next one is right there. Andreas Stöcker and Johann Breit. They will talk about high operational reliability and flexibility for your production with a smart low voltage power distribution. Until then, thank you, Kerem, for your time here in the studio. Thank you out there for being with us and for your questions. And then I'll say goodbye for now.
Take care.